So, hello, welcome in 8th lecture of Humanity 501. So, in lecture number 7, see, so we have proved set of rational numbers is countable set. So, due to network problem, so we stop within 25 minutes. So, let us continue. So, this is our lecture number 8. So, we'll see some more examples on countable set. So, this example number 3. If B is, see, if B is infinite subset of countable set A, infinite subset of countable set A, then B is countable. Then for that, B is countable means every infinite subset of countable set is countable. That is what we do here. So this is our example number 3. So we'll solve this. So solution of example number 3. So what we have given and what we have to prove here. So we have given one countable set A, and if B is any infinite subset of capital A, then surely B will be countable. That is what we have to prove. So here you can consider two cases. Actually, second case is not there. If a set is finite set, then obviously it will be countable. Always it is countable. So what happens if, see, if A itself is finite, then every subset of B will be finite. So in that case, there is nothing to prove. So surely, if B is infinite subset of countable set A, then surely A is also infinite set. So it is countable. So let suppose capital A, it contains countable number of elements. So you can take suppose A1, A2, it goes to infinity. See, B, a countable set. B, a countable set. So it is there. See. So what is our claim? So let, or suppose that, let A be a countable set, and you can write capital B be any infinite subset of capital A. See, then what is our claim? Our claim is that we have to prove capital B is countable. B is countable set. That is what we prove. See, so surely capital B is a subset of A. So since you can write, since, see, capital B is subset of capital A. So already capital B is subset of capital A. So each element of capital B will be in the form of AIs. A1, A2, A3, these are the elements of A, and B is subset of A. So surely all elements of B will be in the form of elements of A. So that will imply, see, each element of capital B is an AI, or in an AIs you can write. See, so what I am considering here, see, means elements of B will be again some A's, small A's. So I'm choosing one by one. So what is next? Let's suppose, see, small n1 B, the smallest, with the smallest subscript, for which, see, for which an1 is element of B. See, I'm taking that first subscript as n1 for which a n1 is element of capital B. All these elements are elements of A. See, next let small n2 be the next smallest subscript for which small a and 2 is element of B, and you can continue this process. See, surely here what you are getting here, small n1 is strictly less than small n2. It is there, and so on. So you can continue this process and so on. So what you will get? So after some steps, you'll get. So then we get what we get a set capital B as, let us see. So you'll get B as an1, an2, then you'll get an3, and likewise. So you get all elements of capital B, and you'll get counting for elements of B. That is, an1 is first element of B, an2 is second element of B, an3 is third element, and likewise. So you can write, see, hence all elements of capital B are labeled with 1, 2, 3, and likewise. Means this is first element, this second element, third element, and likewise. And so you'll get, and so capital B is countable set. So it gives every infinite subset of countable set is countable. See, so next, just a minute. I'm just losing network. Yeah, it's okay. Yeah. Yeah. So next example, that is example number 4. This set of, see, next through that, this set of all rational numbers in close interval 0, 1. I'm taking close interval 0, 1. All rational numbers in the interval close interval 0, 1 is countable. So that is beautiful. set of all rational numbers between close interval between 0 1 or in the close interval 0 1 I've counted. So we'll solve this problem, and you'll solve this problem using last example. So solution, see, so already we have proved, since, see, set of all rational numbers is countable. Already we proved this. So therefore, and see, the set of all rational numbers in the close interval, in the close interval is infinite. See, so using last example, what we get, see, this set of all rational numbers in the closed interval 0 1 will be subset of set of all rational numbers, and set of all rational numbers is countable set. Hence, this subset, infinite subset of countable set will be countable. So using previous example, you will get, so using previous example, what we get, what is previous example? Every infinite subset of countable set is countable. See, we get set of all rational numbers in the closed interval 0 1 is countable. So directly we get what we require, what we have to prove. See, so next example, actually this example is important. So next example, that is example number 5. Yeah, example number 5. Question is that, show that if capital A and capital B are countable sets, then see the Cartesian product, then Cartesian product of A and B, that is Cartesian product A cross B, is countable or is countable set. That is what we prove. So solution of this problem, just a minute. So solution. Suppose what we have given, see, I'm losing network again and again. So just a minute. Just a minute. I'm getting, yeah, no problem. Just a minute. There is a network issue. I'm losing my link. Yeah, just a minute. Yeah. So question is that show that if A and B are countable sets, then see, then Cartesian product A cross B is also countable. That is what is true. See, so solution. So let's suppose since A and B both are countable, so let since A is countable, I can give counting to elements of A. So these are suppose A1, A2, A3, and so on. And similarly, since B is countable, I can give counting to elements of B. So that is B1, B2, B3, B4, and it goes to infinity. So these are countable sets. Hence we are counting. See. So from this you will get both A and B are countable. Hence you can write A and B are countable. So next, what is our claim? Our claim is that we have to prove A cross B is countable. We have to prove A cross B is countable, that is Cartesian product of A and B is countable. See, so what is Cartesian product of A and B? Next, so to prove that A cross B is countable, so let's assume that I'm defining one set. So let's define capital AN, or you can take another set, whatever it is. Yeah, I'm defining capital AN. So let capital AN, it contains all elements of the type it is set. First, let us define it. Capital A, and I'm taking singleton Bn. I'm taking cross product of capital A with singleton Bn. So what is n here? N varies from 1 to and goes to infinity. So you can observe what is A1, what is A2, and likewise. See. So what is this set? Means this set of all order pairs A, B, N, where what is this small a? Small a is element of capital A. So it is there. So capital AN is a set, that is capital A into singleton Bn. So what is Bn? Bn is nth element of capital B. So we are taking cross product of singleton Bn with capital A. So you can observe what will be the elements of, you can just write elements of capital An. So it will be A1 An, sorry, Bn. What is second element? It will be A2 Bn. Third element, that is A3 Bn. Fourth element, it will be A4 Bn, and likewise it goes to infinity. So this is capital An. See, and you can see this is first element, this second element, this third element, this fourth element. You can observe. So it is countable set. You can give counting to elements of n. You can count element of n. So naturally it will be countable set. See, hence you can write. See, then capital An is countable. See, for each n, n varies from 1, 2, 3, it goes to infinity. And what is observation here? And I will write capital A cross B as, let us see, union of n, n varies from 1 to infinity. You can observe what is A cross B. What is an? An, that is A cross singleton Bn. So if you take, see, A cross B1 union A cross B2 union A cross B3 union, and it goes to, so you get all elements of A cross B. So naturally, so this union provides us whole Cartesian product A cross B. So naturally A cross B will be countable union of countable sets. Since you can write, see, since countable union of countable sets is countable, so therefore, see, A cross B is countable, and that is what we have to prove. So this solution of this problem. So next problem, actually it is sixth problem. So example number 6. What is example number 6? See, show that if B is, capital B is countable subset of an uncountable set. If capital B is countable subset of an countable subset of an uncountable, just yeah, there are some network issues, so I'm not getting those things almost. Yeah, just a minute. Yeah, so what are to prove here? Show that if B is countable subset of an uncountable set capital A, see, then A minus B is uncountable. That is what to prove. Then A minus B is uncountable. See, so solution of this problem. Actually, capital A is uncountable, B is countable subset of A. So you can observe, see, if we draw a figure for this, so there's no need to use fixed shapes. Suppose, see, so this is capital A, and suppose this is capital B. So capital A is uncountable. See, and B is countable. And this is A minus B. What we have to prove? A minus B is uncountable. So here, on the contrary, so let us assume that. Suppose, so there is no need to draw this figure. Suppose that capital A minus B is countable. See, so on the contrary, I am assuming that suppose A minus B is countable. What we have to prove? A minus B is uncountable. So because of that wrong assumption, so you will get something wrong. So suppose that A minus B is countable. So next, then see. So then what we have? I can write capital A equal to A minus B union capital A. Already, so yeah, sorry. So it should be capital B, A minus B union B. See. So capital B is already countable. That is we have given. So it gives that. See. It gives that capital A is union of two countable set. Already B is countable, and we assume that A minus B is also countable. So naturally capital A will be countable union of two countable sets. Sorry, union of two countable sets. And naturally it will be countable. So countable union countable is countable. Hence, see, capital A is countable. So what we get? Because of that wrong assumption, we get capital A is countable, but A is not countable. It is uncountable set. So which is contradiction? See, which is contradiction do? Capital A is uncountable. So already capital A is uncountable set. Hence our assumption is wrong. So therefore, see, our assumption is wrong. If assumption is wrong, then what is correct? See, hence we will get, hence A minus B is uncountable. It should be uncountable. If it is countable, then we are getting contradiction. Hence, and therefore it is solution of this problem. So next, so this is about countable set. So next topic, it is real numbers. So in that we'll prove set of real numbers is uncountable set. So we'll stop here. In next lecture we'll continue. That is lecture number, yeah, See, in next lecture, that is lecture number 9. So we'll see next topic, that is real numbers. So stop here. So hope you are watching all these videos in series. Please watch all these lectures in series. So don't watch directly lecture number 9 or 8. So you have to, yeah, carefully watch all lectures one by one. So then you get all these things. Otherwise, you will not get. So I will stop here.